in the Antarctic ice coverage. When it comes to volcanism, volcanoes affect the climate also by spewing ash, but more importantly, sulfur dioxide high into the atmosphere. And when it gets high up, 80 to 100,000 feet or more, it has a long lifetime, and it quickly gets converted to what we call sulfate aerosols that act like little mirrors to reflect the solar radiation that comes from the sun back to space. And the result is that less sun energy gets through to warm the surface. And we wind up with 3-4 years of cooling. And that's been clearly seen in the temperature records in the 80s after El Chicon and Mount St. Helens, and in the 90s after Pinatubo. In times of very low stratospheric or high-level sulfate aerosols, like we've had in the early part of this decade, the atmosphere is cleaner and more radiation gets through, and we wind up with a warming. So some of the changes that we've seen in the last 2 decades can be explained by volcanism in the atmosphere.
Why do you think, not to derail the scientific part of this, but why would something NOAA, and can someone explain who NOAA is?
They're the National Oceanographic and Atmospheric Administration. That's our government agency responsible for studying and reporting data on the oceans and the atmosphere.
Okay, thank you. You know, they say, NOAA has said that 80% of volcanoes are actually underwater. I didn't know that. I don't think the public would know that. So when you talk about volcanism, volcanoes being a key, one of the keys, impacting climate, I'm stupefied that it's off the table of human consumption and awareness as being a huge impactor of, warming the oceans, but also altering weather.
Kim, can I come in on that?
Please do.
Okay, because when NOAA said that 80% of volcanic activity occurs underwater, I first heard about that in the early 1990s when I began researching for the book. But, that was in 1991. In 1993, at that time in 1991, NOAA thought there were about 10,000 underwater volcanoes in the entire world. That was 1991. 1993, they discovered another 1,133 underwater volcanoes down off the coast of Easter Island. They were shocked. So they increased the world's supply of underwater volcanoes by 10% in just a matter of months. They also discovered underwater volcanoes, rift volcanoes off the coast of Oregon, off the coast of Washington, that they weren't really aware of. Now that was 1993, so they thought there were 11,000 underwater volcanoes. Now, if you visit NASA's website, they estimate that there may be as many as 3 million underwater volcanoes. It is incredible how the knowledge has changed since 1991.
Well, do you think, I guess my question on this is, and I just want to stay on it till I have a clear sense of this for the public, if that's true, even if it's true by 20%, isn't that going to impact ocean warming critically?
It has to impact it. There's, and the fact of the matter is that volcanism has increased. My understanding is that above water volcanism has increased in the last 100 years, and that if underwater volcanism has increased, I would assume that, if above water volcanism has increased, I would assume that underwater volcanism has increased even more. So what we're looking at is that the above water volcanism is pouring ash and sulfur and everything else into the sky, which is cooling the skies, while at the same time the underwater volcanoes are heating the water and sending more moisture into the sky. So you have more moisture rising into skies that are cooler, which to me is a recipe for disaster.
Let me ask you this. If the glaciers are growing, I want to go back to the glaciers for just a minute. What are the tools or what are the instruments or who are the people that measure the glacier growth or recession? Who are they?
Well, first, let me just mention how many more glaciers are growing than we're being told about, because glaciers are growing in New Zealand. All 50 glaciers are growing in New Zealand. Glaciers are growing in Greenland, at least growing thicker. Glaciers are growing in Antarctica. Glaciers are growing in Iceland. They're growing in South America. There's the Pio 11 glacier. It's the largest glacier in Chile. It is growing. The Perito Moreno Glacier in Argentina. It's the largest glacier in Argentina. It's growing. Glaciers are growing on the tallest mountain in France, Mont Blanc. Glaciers are growing in Canada on Canada's highest peak, Mount Logan. But, they try to cover this up. The article I read about Mount Logan, it said that Mount Logan was growing taller. Satellite measurements show that Mount Logan is growing taller. You had to get about 5 paragraphs down into that article before you discover the reason it's growing taller is because there's more ice accumulating. So
I didn't know that ice had anything to do with mountain growth.
Well, it only in the respect of measuring it with satellite measurements.
Gotcha.
So it's the mountain itself is not growing, but the satellite measurements show that something's there, so it's ice.
Okay, can we bring in Dr. Tim Ball? Tim from Canada, who is a climatologist trained out of London, England, who is also a teacher and a writer for Canadian Free Press. Dr. Tim Ball, thank you. Amongst many other things.
Yeah, well, thank you, Kim. It's very interesting to listen to all of this because, of course, I've watched for 40 years the evolution of climate and climate science. And what's interesting is that meteorology is actually a subset of climate. It's the study of physics of the atmosphere. And just to clarify some things for the public, when they stand outside, they experience weather. And that weather is what scientists call a white noise. That is, it's the sum total of a whole bunch of individual noises that scientists call red noise. And each of those red noises, and you're discussing some of them here, the volcanoes and the ice, glacier, and so on. But that white noise that is the weather is everything from cosmic radiation in deep space to what you're also discussing, and that is the heat off the bottom of the oceans. Now, that's collectively called geothermal heat. When you discuss it as volcanoes, that leaves the impression in the public's mind that it's individual volcanoes. It is, but the public also need to know that there are what are called mid-Atlantic or mid-oceanic ridges, long ridges of where very thin crust of the earth and a lot of heat from inside the earth is being put into the oceans as well. If you're going to understand the weather, what you experience, and the analogy I'd like to use is not particularly good, but it's like standing outside of a football stadium with 500,000 fans all cheering, and the noise you hear is the collective noise, the white noise, that's the weather. But what we're trying to do is identify individual noises from within that stadium. And it is that complex, and that's why it's so difficult. Now, that's weather, and that's what you experience at any moment or during a day. But climate is the average of that weather over time or in a particular region. And one of the difficulties is that studying weather is difficult enough because you've got Joe as a meteorologist and so on. But the study of climate is a generalist discipline. In other words, you've got to bring together all of the expertise of everybody who's studying cosmic radiation to studying the sun and on and on and on, and bring that all together. And the analogy I like to use is that the climate is the full picture. But what we've got in today's world, because of specialization, is individuals who've got one piece of the puzzle.
Kind of like touching... Dr. Ball, kind of like touching an elephant and you touch one part of its body and you have your eyes closed and you say, I'm touching a tree. Yeah. And your eyes are closed and you're touching one part of an elephant and you think you got the whole thing.
Okay, and of course they've made that even worse because, as you and I discussed, they've got the focus on CO2, which is one very, very, very small part of the total weather and climate system, and they've been able to focus attention on that, get the world's attention on that, and that's a question that people need to ask themselves. But back to my original point about weather and climate, Bob mentioned Milankovitch. Well, I recall at the beginning of my career, you go to conferences, and if anybody dared to suggest that the Milankovitch fit was an explanation, they got attacked immediately.
What are you talking about? Hold on 1 second. We got to take you back because you're very much within your discipline and gestalt of understanding. And you can go 100 miles an hour. We want to stay very, very slow with the public who needs the grounding, and so I just want to bring you back and talk about what is it called, the
Milankovitch.
The Milankovitch.
Yeah,
Say what it is.
Yeah. Well, he was a Yugoslavian, Serbian actually, scientist who realized that the various Sun-Earth relationships were a critical factor in determining the weather and the climate that we have on Earth. Now, this is not a new idea. I mean, the first people to look at changing orbit of the Earth as it affects the climate was a Scottish scientist by the name of James Kroll. And 150 years ago, he was calculating how the changing orbit of the Earth, caused by the gravitational pull mostly by the gravitational pull of the planet Jupiter, would affect the amount of energy the Earth received over time, and then therefore that would affect the weather and climate. And so Milankovitch, and then a little bit later on, about 130 years ago, they realized that the tilt of the Earth is constantly changing, and I'm not just talking about the wobble, the actual change of the tilt. We say it's 23.5, but as I like to joke, that's just close enough for government work. But what Milankovitch did was Milankovitch brought all of these things together, and he did his work in the 1950s, and incredible the amount of calculations that he did pre-computer, and it came up with how the amount of energy the Earth receives varies with the combination of the changing orbit, the changing tilt, and something called the precession of the equinox. And that gave an average of variation of the amount of energy that the Earth receives from the sun. And, of course, that was plotted, and Bob talked about Ewing. And Ewing and Don had a theory about Arctic ice, but there was another book that came out about 1970s called The Deep in the Past. And this was a sort of a trade book that was trying to link those deep sea sediments that Bob talked about with the glacial weather patterns. But as I said, Milankovitch still wasn't accepted at that time. I recall 1989, a conference where somebody presented Milankovitch and nobody questioned it. And so I knew that at about that time, the whole Milankovitch concept as just part of the cycles of the weather system was generally being accepted. And I think that one of the things that you're hearing from Bob and from Joe and so on is how recent not only the weather records are. I mean, we're talking about Arctic ice, and it's really only valid data from 1979 to the present time, and yet the Earth's 5 billion years old. And then also the fact that so many of these mechanisms and things, I mean, I watched the introduction of the El Nino. It started as the Walker circulation, and then it became the Southern Oscillation, and then it became El Nino, Southern Oscillation, and on and on and on. So I would like to say that with the climate puzzle, we haven't even got the four corner pieces, and that's how you do a puzzle. You find the corner pieces so that our understanding of the oceans, our understanding of the atmosphere, our understanding of the land surfaces, and the understanding of space.
We are in space.
Yeah,
I mean, this is another thing.
Those, and then when you start talking about the edge pieces of the puzzle, they're simply not there. Now, just to finish up on the geothermal thing, I mean, I wrote a textbook published in 1987 was the first edition, and I had a reviewer. I put in there that, geothermal, that is the volcanic under the ocean, should be considered, and a couple of the reviewers just rejected it. And I still put it in the book, but these ideas of because all the textbooks assume that the only source of energy for the Earth's atmosphere and weather is the sun.